Okay, thank you for your patience. This is part B. We'll see if we can get this to record as well. Example 3, I want to know the solution to 2 to the 2x plus 5 equals 16 to the x minus 7. We can do this algebraically or graphically. Okay, algebraically, we need to make the basis the same. 2 to the 2x plus 5 equals, I can replace that 16 with 2 to the power of 4. And my rules of powers on the right side would be power of a power. I'm going to multiply. So I have 2 to the 4x minus 28. If I have an equality with the basis the same, that means the exponents must be the same. So 2x plus, I say so too much, that's why I wrote it down. 2x plus 5 equals 4x minus 28. We need to solve, get all the x's on one side, the numbers on the other. So I'm going to add 28 to both sides. 33, 2x. I'm going to subtract 2x from both sides. Divide both sides by 2. Now we'll get 16.5. Let's solve this graphically now. I'm going to type in the two equations. Apparently I'm going to clear first. All right, the two equations. Y equals 2 to the 2x plus 5. So I'm going to put my left side in, being careful to put my exponent in brackets. And the other one is 16 to the power of bracket x subtract 7. Remember that these things grow hugely, exponential growth. My answer is going to be very large. So we're going to adjust our windows. We are going to include a bit more of the x values and know that our y max is going to be huge. I'm just making an educated guess and see what we can see. First graph. Second graph. We can see that the one on the left, the 2 to the 2x plus 5, is less steep than the one on the right, 16 to the x minus 7. So they will intersect somewhere up there, we just can't see it. Well, we can keep playing with the windows, or we can just see if the graphing calculator will find the point of intersection, even if it's not on the screen. So let's try it. Second function calc. The option I want is number 5 for intersection. I need to see which curve I'm on. I'm just scrolling along. There it is. Scrolling along. It's on the left curve. Enter. Make sure that it's on the right curve. There it is. I can see it. I saw it. Where'd it go? There it is. I'm on the other curve. Enter. Guess. Enter. And this should give us the point of intersection. I tried to find the point of intersection with this very equation before when I hadn't adjusted the windows, and it didn't work. So there we go. Point of intersection is 16.5, comma, 2.74 times 10 to the 11. So that is almost a billion. All right. 16.5 is our x value. We can see it graphically or we can see it algebraically. Example number 4. We have 3 to the 3x plus 2 equals 15. Algebraically, this one would be very difficult. I cannot rewrite 15 as a power of 3. So we are going to solve this graphically. I am looking for the point of intersection of the lines y equals 3 to the 3x plus 2. Sorry, that is a function, exponential function, and the line y equals 15. And the point of intersection will give me the solution to the problem. So for my y1 equation, I want 3 to the power of 3x plus 2 bracket. I want to see where it intersects with the line y equals 15. Now I need to think about my windows. I can see that exponential function, but I can't see the line y equals 15. So I definitely need to adjust my windows so that I can see more of y max. So I don't know, 25. That's an educated guess. I'll be able to see the line y equals 15. Let's find the point of intersection. Second calc, 5 for intersection. First curve, I believe I'm on the curve. On the line. Enter. There it is. 0.15 comma 15. So the solution to the problem is x is approximately equal to 0.15. Notice we've got a whole lot more decimal going on there. Let's just check that that is in fact correct. What is 3 to the 3 times 0.15 plus 2? 3 to the 0.45 plus 2 is approximately 3 to the power of 3. So 0.45 plus 2 is 14.76. So close to 15. If we hadn't rounded quite so, we would have the solution to the problem. A place where we would really want to compare and find points of intersection is when we're dealing with investments. So if we have two different scenarios and we want to find out where they're the same, we're looking for a point of intersection. So we're going to have two rather different scenarios at these two banks and see where the investment would be equal. So at TD Canada Trust, someone goes in with $1,000 and can obtain 9% per annum. At the Royal Bank, someone else goes in with more money, but can only achieve a 2.5% per annum rate. When are they the same? All right, first we need two exponential equations. The amount of money in the account is initial value, which is 1,000, and the rate, remember this is a growth rate, so it needs to be bigger than 1. We have our 1.09. X is the number of years you leave it in the account. We're going to get more into money a little later. The amount at the Royal Bank, initial value is 2,000, but the rate is smaller, 2.5%. Let's find out where they intersect. So for the first equation, I'm going to type in 1,000, my rate of growth, to the power of x. For the second, initial value, rate of growth, to the power of x. Now I know full well I wouldn't be able to see that on my grid. I need to adjust my windows. Time is in years. I think it may take a few years for those both to be equal. So I'm going to go with, well, 20 years. I'm talking about a lot of money. Well, a decent amount of money, but definitely more than 25 bucks. So let's go with $5,000. We should be able to see that on our graph. So there is the TD equation. It's growing exponentially at 9%. And there's the Royal Bank. Starts with more, but the rate of growth is smaller. There's the point of intersection. Let's get the calculator to tell us where that point of intersection is. Point of intersection is about 11.3 at 2641.95. So in 11.3 years, both investments will be at $2,641.95. I have a handout for you, Crossing Curves, it's called, and page 72, 1 to 4 would be excellent.